Welcome everyone. So, in this lecture we are going to compute the simplicial homology group for some simple topological spaces. So, before doing that, let me give one convention that I want to mention here. So, if I look at the homology group of a simplicial complex, let me write it here. So, suppose X is a simplicial complex or a delta complex, let us say it is a delta complex. Okay. So, then corresponding to this I can construct what is called Cnx. Okay. Now, I can define this delta n from Cnx to Cnn n minus 1x. Okay. Up until the 0th stage, because we do not have anything beyond C0. Okay. So, the convention is delta 0 is the 0 map. This is the convention. So, delta 0 is a map from C0. We can think of the 0 group. Okay. And so, therefore, the 0th homology of X would be simply C0 by image of delta 1. This is a convention, you can think of it as a definition. So, whenever we have scenarios when we try to compute the homology groups, just put C0 and then put 0 group on the right hand side, define delta 0 to be 0 map and you get the kernel. So, with this convention, let us compute the homology group of some spaces. So, the first one is just simply a point. So, X is simply your point V. So, you have this C0 of X, which is just a free module generated by V, or it is an abelian group generated by a point V. And so, I am going to focus only on Z coefficient. So, F for me is Z in all these computations, because this won't be much relevant. So, in this example, we get C0 of X is just generated by one element, and then everything else is trivial group. Okay. So, all I have is this picture where I have this C1x, C0x, and then here I have the 0 group, here I have the 0 group. Everything else on this side is 0, so automatically the homologies of higher dimension automatically become 0, because we have only 0 groups, every subgroup of 0 is 0. Here I have the boundary map, here I have the 0 map. So, all I have to check is what is the image of delta. The image of delta is 0, because it is a 0 map. So, H0 of X is just isomorphic to C0 of X, which is just isomorphic to a group generated by one element, abelian group generated by one element, which is Z, and everything else is 0 as a group isomorphic to 0. Okay. So, what we have understood here is, if I take a point, then its 0th homology group is isomorphic to Z and everything else is 0, every other homology group is 0. Let us go to the next example, which is circle. So, I am putting a simplicial complex structure or delta complex structure in this case on circle, okay, with only one vertex. So, V is only one vertex, this is my one map, and only one edge, call this A. Okay. So, what is the simplicial complex, or is the simplicial chain complex structure here or delta chain complex structure here? C0 of X will be the group, abelian group generated by the element V. Okay. And C1x, so this is isomorphic to Z, C1x will be generated by the element A. Okay. And every other thing is 0. So, you do not have any other simplices, n dimensional simplices for n greater than equal to 1. So, everything else is simply greater than equal to 2. So, everything else is simply 0. So, if I look at the chain complex, it will look like this. So, I have C0, which is generated by V. Here I have the 0 map. I have delta 1, which is C1x, which is generated by A. And then I have delta 2, which comes from 0. So, on this side everything else is 0. Okay, everything else is 0. Okay. So, all I have to worry about is what is happening on this stage and this stage, everything else is 0. Okay. So, on this side I can write down that if I am looking at Hn of x, then n greater than equal to, so this is the 0th step, this is the first step. So, n greater than equal to 2, everything else is 0. This is just 0, everything else is trivial. Now, let us look at n equal to 1 and n equal to 0. So, I am going to look at n equal to 1 and n equal to 0. So, in n equal to 0, what do we have here? We have that this is just image of delta 1 z quotiented by image of delta A. Now, if I look at boundary of A, simplex A, this you can think of as a map from V0 to V1 to this space here, where both V0 and V1 goes to the same vertex here. So, when I am looking at the boundary of it, this will be the class of V minus the vertex V. So, this is 0, delta 1. So, delta 1 is 0 map. Okay. So, once I get that this map is 0, this is also 0 map. So, the kernel is everything, image is nothing. So, kernel by image is just the kernel which is generated by V, which is isomorphic to Z. So, this thing is isomorphic to Z, this is isomorphic to Z. So, this thing is simply isomorphic to Z. Okay. H1 is x is kernel of delta 1, sorry, H0, right, this is H0, sorry, H0 of x is C0 x image of delta 1. Delta 1 is 0 map because on the basis it gives you 0. So, this is just isomorphic to Z. Now, let us look at H1. Okay. So, I am looking at the stop which is C1 now. Okay. So, I have to compute the kernel of delta 1 and image of delta 2. Okay. Delta 1 is a 0 map. So, the kernel of delta 1 is everything. So, the kernel of delta 1, so this tells you kernel of delta 1 is exactly C1 of x. Okay. Delta 2 is a 0 map. So, the image of delta 2 is 0. Therefore, H1 which is kernel of delta 1 which is C1x which is Z quotiented by 0. So, this is isomorphic to Z. Isomorphic to Z. So, for circle we have seen that 0th homology group is Z, first homology group is also Z, n greater than equal to 2 homology group is 0. Let us look into a bit more complicated example which is that of torus. So, for torus we have this simplicial structure where we have these objects, and I am going to write down the simplicial complex structure here. So, let me put it put this discussion at the top a little bit. So, what is the simplicial complex structure? Here the simplicial complex structure is the following. C0 is C0 of, so let me write this x equal to t. So, C0, I am not going to repeat this t again and again. So, C0 is generated by V, that is isomorphic to Z, generated by one element. C1 is isomorphic to abelian group generated by 3 elements A, B, C. Okay. So, now I can use them as a standard basis saying that it is generated by A, B and C, or I can use their formal linear combination to call that okay, I have a basis element which is generated by A, B and A plus B minus C. Okay. This is, so if I have a free group generated by a free abelian group generated by A, B and C, so then I can take the linear combination of A plus B minus C, and then every other element is a formal linear combination of A, B and A plus B minus C. So, this is just a vector space notation that I am using. So, these 3 generate C1x. So, this is 3 copies of Z, 1 copy here, 1 copy here, 1 copy here, with these are the basis elements. Okay. How about C2 of x? C2 of x is generated by two elements U and L. Okay. Right. So now I have the spaces, now I want to get the map. Okay. So delta 0 is 0, that is our convention. Delta 1, in this case I have to compute delta 1 on these three objects A, B, A plus B minus C. Okay. So what is delta 1? Delta 1 let us compute to A. Delta 1 on A is 0. Okay. So if this is difficult, you can think of C1 as generated by A, B, C also. Okay. So delta 1 at A is 0 because you have only one vertex, anything minus anything is 0. Okay. Delta 1 at B is also 0. Well, again the same logic, the endpoints are same. Delta 1 of C is also 0. That means delta 1 is 0. Okay. So therefore H1 is, so the H1 is C0, C1. So let us look at H0 first. Let me look at H0 of x. So this will be simply C0 quotiented by image of delta 1. Image of delta 1 is 0, so this is simply C0. C0 is isomorphic to Z. So n equal to 0, I get Z. Okay. N equal to 0, I get Z. Now let us look into H1. Okay. So for that I have to compute delta 2. Delta 1 I have seen it is 0. Now I have to compute delta 2. So if you look at delta 2 of U, the upper one, that will give you A plus B minus C. Okay. Similarly, delta 2 of L is A plus B minus C. Okay. So therefore, delta 2 of U and delta 2 of L is, the image is generated by this element A plus B minus C. Okay. So then if I look at H1, so let us look at H1. If I look at H1, okay, this is kernel of delta 1. Delta 1 is 0, so the kernel of delta 1 is everything. So this is C1, this is generated by A, B, A plus B minus C, quotiented by the object which is on the image of it. This is generated by A plus B minus C. So you have this abelian group on the top which is generated by A, B and A plus B minus C. You are quotienting by the abelian group generated by A plus B minus C. So we will end up with the abelian group generated by simply A and B. Okay. So this is just two copies of Z. Therefore n equal to 1, the first homology group is Z direct sum Z. Just two copies of Z. Now what about H2? So delta 3 is 0 because C3 is C3 onwards is 0. So let me write it down here. C3 is 0 for all n greater than equal to 3. So delta 3 is 0. All you have to compute is kernel of delta 1 because delta 3 is 0, that means image of delta 3 is 0. So all you have to do is kernel of delta 2. Okay. So what is the kernel of delta 2? So let us say you take delta 2 acts on some element Pu plus Ql. This will be P plus Q, A plus B minus C. Okay. This is 0 if and only if P is equal to minus Q. That is it, that is the only condition. This element is 0 if the coefficient is 0 and the coefficient is 0 if they are of reverse angle, reverse sign, Pn minus C. Okay. So therefore, the kernel of delta 2 is generated by U minus L. That is just one element. Okay. So therefore, H2 of x is generated by U minus L. This is quotiented by 0. This is just simply generated by U minus L. Okay. So therefore, H2 is also isomorphic to Z, just isomorphic to U minus L. Okay. Now let us go to a bit more complicated example, which is that of RP2. And this is the first time where we will see that other than getting abelian group Z or direct sum of Z, we can get something which is the quotient of Z also. Okay. So let us first write down, we will work this out. So let me just get this, put this thing later, here somewhere, maybe later on. Okay. So let us just start with the simplicial structure and see what are the C0, C1 and C2x. Okay. So let us start with C0, that is generated by V and W. C1 is generated by A, B and C. C2 is again generated by U and L. Okay. And C3 onwards, everything is 0. Okay. So as usual, delta 0 is 0 by the convention. Okay. So now I want to compute what is delta 1. Okay. So now if you look at delta 1 and you apply it to A, B or C, one of them. Okay. So let us say delta 1 of A will be W minus V, delta 1 of B will also be V minus W, and delta 1 of C is V minus V, which is 0. Okay. So therefore delta 1 of A is generated by this element W minus V or V minus W. Okay. So then I look at image of delta 1, this is generated by W minus V. Okay. Right. Correct. So therefore if I want to look into H0, that would be C0, which is generated by V and W, quotiented by W minus V, which you can simply think of as V, W minus V, quotiented by W minus V. So that's just a copy of thing generated by V. Okay. So therefore H0 is isomorphic to Z. Okay. Now let us look into H1. Okay. So let's look into H1. Let me copy the photo here. Maybe this I can put somewhere later on. This thing. Maybe I can put it here. Let me see if so. Let me put it here. Okay. So let us look into the picture again and let's see what are the objects that we can get. So let me put this copy of this picture on this page also. Copy of this picture, this page also, and let us try. So far we have obtained what is called the image of delta 1 and what happens to delta 0, which is by convention 0. So now let us look into delta 2, the map delta 2. That is going to be interesting. So delta 2, you can see that delta 2 of U is minus A plus B plus C. So this one, if I go via this convention, so this is C is going in the same direction, B is going in the direction, A is coming in the reverse direction. So this is minus A plus B plus C. But L happens to be the following. L happens to be, if you are going like this way, you are going C A and minus B. Okay, so A plus B minus C. So we have the overall convention of A plus A, B and C, and with this direction I am getting that this is getting A minus B plus C. Okay. So therefore delta 2 of U gives me something non-trivial and delta 2 of L also giving me something non-trivial, and these two are not related to each other, they are not reversals of each other. Okay. These are completely different objects. So if what you get is the following. So if you look at let us say lambda into minus A plus B plus C plus mu into A minus B plus C, if this is 0, this will tell you that first of all mu minus lambda equal to 0, so mu equal to lambda, and then it will tell you mu plus lambda is equal to 0. So, this will tell you mu equal to lambda. Okay. So, therefore, these two as different images, and therefore, if it is going to independent object, these are not linearly dependent, if you want to use that terminology. Therefore, this map is injective, delta 2 is injective. So, once delta 2 is injective, what happens is, if delta 2 is injective, if you look at C2, C2 has dimension 2, that has 2 generators. So, the image will have 2 generators. Okay. On the other hand, if you look at kernel of delta 1, so this we have computed, delta 1 is W minus V, which is V minus W. Okay. So, if you look at kernel of delta 1, so if you look at kernel of delta 1, first of all, C goes to 0, delta 1 of C is equal to 0. Okay. And then secondly, if I look at A minus B, that under delta 1 is going to 0. Okay. So, therefore, kernel of delta 1 is generated by A minus B and C, which I can write generated by C and A minus B plus C, it is the same thing. So, we have obtained kernel of delta 1, which is generated by this, and image of delta 2. So, the delta 2 is injective. So, the image would be generated by the image of delta 2 under U and delta 2 under V. So, image of delta 2 is minus A plus B plus C and A minus B plus C. So, I can write this as a generator which is generated by A minus B plus C, and then I add these two up, which will give me 2C. So, this is generated by A minus B plus C and 2C, image of delta 2. So, now if I look at kernel of delta 1 by image of delta 2, that is H1 of x, what do I get? At the top, I get a space which is generated by a group which is generated by C, A minus B plus C, and the bottom I get something which is generated by A minus B plus C and 2 of C. So, this is isomorphic to group generated by C, quotiented by 2 of C. This is Z on the top, quotiented by 2Z at the bottom. So, therefore, this is isomorphic to Z direct sum 2Z, quotiented by 2Z, which is isomorphic to Z2. Okay. So, in particular, H1 of, let me cut it from, H1 of RP2 is isomorphic to Z2. Okay. And now, if you look at delta 2 is injective, therefore, the kernel of delta 2 is automatically 0, therefore, H2 is automatically 0. So, H2 of RP2 is automatically 0. Okay. So, this example we have seen that the homology group of a space can have torsion also. Okay. It can be finite order also. It is not necessarily always Z direct sum Z. Okay. So, this example is quite interesting. This is RP2, where we have seen the 0th homology of Z, the first homology of Z2, and higher homologies are 0. And you can see all of these examples, the 0th homology is always Z. In this one, 0th homology is Z, 0th homology is Z. No matter what we are doing, the 0th homology is also always Z. And so, this is the reason, because this is a connected space, the 0th homology will have only one component, and we will show later that if I have n connected components of a space, then my 0th homology will have n factors of Z, each one correspond to each connected component. Okay. So, we will see some properties of simplicial homology groups in our next lecture. Thank you.